All right, so we have spent some time going into like the history of the atom and where these ideas are coming from, right? So we went from like clay to everything's made out of fire to finding that there's positive things, finding that there's negative things, a nucleus. Oh my gosh, things are moving, right? All these different models, all these different ideas, leading us to what we know to be true about what's going inside the atom right now. And so what we're going to look at now is, okay, what are those little pieces in there that these scientists have spent all of this time discovering? What are their purposes? Why do we need them? Things like that. And it's going to lead us into bonding and all this great stuff. Has to do with these really tiny little things inside the atom. So with that, let's go ahead and get started. Okay, so inside the atom, right, we know that matter itself is made up of atom, right? We've talked about how it's anything that has mass and occupies space. So what is occupying that space are atoms. And so we have talked about how atoms are these little teeny tiny things that originally we thought were indivisible and discovered that was not the case, right? That we can actually break these things down. But what's really important to understand about atoms versus breaking them down is this next statement where it says it's the smallest particle of an element. Yes, there are smaller things, protons, neutrons, electrons, but the atom itself is what identifies the element, right? So an atom of carbon is different than an atom of gold, which is different than an atom of silver. Protons, neutrons, and electrons are in there, but they are making the atom, and it's the atom that identifies that element. And the atom of an element is going to stay the same even in a chemical reaction. So maybe it bonds with something differently, it changes its state, matter, whatever that might be. But if you're starting a chemical reaction with atoms of carbon, you are finishing that reaction with with atoms of carbon. That's not going to change, okay? And so the identity of those atoms stays the same in our chemical reactions. So within our atoms, right, we have these subatomic, right? Sub meaning within or under particles. The electrons, protons, and neutrons, right? And it took a lot of scientists a really long time to figure all of those different things out. And so we have these things now. And so as you understood from all of those different models, we know that electrons are negative, protons are positive, and neutrons are neutral, right? Think neutral, neutron. Okay, and so we have those charges. And so for the symbols involve their charges. So for an electron, it's a lowercase e and a negative, a lowercase p and a positive, and a lowercase n and a neutral sign. Please make sure you're using lowercase symbols. We don't want to be talking about a positively charged phosphorus or a neutral nitrogen or whatever, right? So capitalization, things like that, keep in mind, we got to use that straight. Keep that straight in chemistry, all right? So in terms of their relative mass, we are talking about like teeny tiny things, right? Like so small, like times 10 to the negative, bajillions, okay? And so we use the word relative mass because we didn't want to keep talking about these things with like crazy exponents that are so small that didn't make sense. And so we have a unit that we use when we're talking about subatomic particles called an AMU. Atomic mass unit, okay? And so for an electron, we say that relative mass is 0 AMUs, a proton is 1 AMU, and a neutron is also 1 AMU, okay? And again, these are relative masses. We're not talking about grams, okay? A proton doesn't weigh a gram, no way. And so where these things are, right, that was the whole point of these models. They were discovering these subatomic particles over time, and they were able to locate where these subatomic particles are going to be located. So our very current model of the atom talks about how electrons are in that electron cloud. And so if you remember, we said that electrons are moving like super fast, right, all over. And so if you picture like a propeller or a fan when they are moving super quick, it kind of looks like there's like a solid sheen, like it's not solid, right? There's the propeller blades, but it looks solid. That's because what you're looking at is those fan blades moving so fast, it kind of creates that like haze look. Same thing is true about electrons. That's where it's got its name, the electron cloud, because those electrons are moving so fast that it creates that sort of like haze circular look as well. And then our protons and neutrons, we know that those friends are in the nucleus. So let's dive deeper a little bit and talk some more about the nucleus. So the nucleus is going to be in the center of the atom, and it only contains the protons and neutrons. Again, the electrons are cruising around on the outside. So our nucleus, center of the atom, it is being held together and held in the middle of the atom by something called the strong force. Okay, that's what's going on in that part. Okay, oh, I didn't mean to move the picture. Right there, strong force. Okay, again, so it's holding that atom, or holding that nucleus together and keeping it in the middle of the atom. The other thing to think about as we talk about the nucleus is the fact that it is only containing protons and neutrons, and therefore it is responsible for the mass of our atoms, right? If you think about it, again, electrons, we said, don't have a mass, and they're moving around on the outside, and so they are not coming in. So it's incredibly important to note that the mass of an atom is contained in its nucleus, okay? All right, then, so when we think about what is making all of these different elements so different, right? We've talked about atoms, protons, neutrons, and electrons. They all got electrons, they all got neutrons, they all got protons, but what makes these elements different is the atoms themselves, okay? The way that these things are coming together, the way that they are made, that is what's making those elements different, the atoms themselves. Okay, so atomic number. Atomic number is going to be something that is located on the periodic table, so let's pull that up. So again, when you look, you see these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those little numbers that are in order, like as you go through the periodic table, those are your atomic numbers. And so the atomic number for nitrogen is 7. The atomic number for oxygen is 8. Okay, so as you thought about that question, the answer is no, hopefully, is what you said. It cannot change, right? Calcium is right here. It's written, it's permanent, it's on there, it's the same periodic table all over the world. Those atomic numbers are not changing, okay? They stay where they are, okay? Then the reason we like the atomic numbers, all right, is they actually tell us how many protons are in an atom. So when you're looking at a periodic table, you know, great, iron has 26 protons, sulfur has 16 protons, fluorine has 9 protons, okay? And again, these numbers cannot change. Carbon has 6 protons. As soon as there are 7 protons, well, now you're talking about nitrogen, okay? So the number of protons for an element cannot change. And the number of protons for an element identifies what that element is, right? So go ahead and think about this, right? And this is why it's so important for us to know our elements and symbols, because you have to be able to say, okay, barium is Ba, and then find Ba on the periodic table. You will get faster at this, but here's Ba, it's element 56, boom, that means it has 56 protons. Okay. So then we have something that we call mass number. So mass, right, we talked about at the beginning, the relative mass of these subatomic particles. Electrons were 0, protons are 1, neutrons are 1. Therefore, your mass number is going to, in fact, be the sum of the protons plus the neutrons, okay? So again, scientists are lazy. We just like to write it like that, okay? It's your protons plus your neutrons. That's what's going on there. Okay, so mass number equals protons plus neutrons. And we also know then that the number of protons, that also is equivalent to the atomic number. All right, so with that in mind, what I would like for you to go ahead and do is type in what is the equation for atomic number using these information that you already have. A big part of this unit is going to be algebra, okay? Reworking these little equations. So take a second, think about it, and tell me what the equation for atomic number is going to be. All right, so these mass numbers, again, these are something you are adding together, these protons plus neutrons, the atomic number with the neutrons, whatever it might be. And what you can see here is it's actually going to be part of the name. So you may have even heard a scientist talking about like carbon-14 versus carbon-12, or they talk about diamonds or graphite or charcoal, whatever it might be, right? So when they're saying that number after the name, that number is in fact the mass number. Okay, so in this example right here, aluminum 27, that 27 is telling us the mass number. And do keep in mind, if you know the name of the element, then you know the symbol of the element. And so then you can go to the periodic table and you can get the number of protons. Okay, do not forget these things, protons, there we go. All right, name, symbol, periodic table, atomic number, boom, that's your number of protons, right? Think through that thought process that way. So in the name aluminum-27, we now know that the number of protons is 13. We know that the mass number is 27. We can simply take that 27 minus 13, and that equals our number of neutrons. Okay, so again, reworking the algebra, solving these things out. Okay, so that 27, the mass number, is part of the name. All right, so now let's take a look at these examples. So again, remember that calcium, the symbol is Ca, and this 41 right there in the name is our mass number. So I know the mass number is 41. Great. Calcium is a symbol, it has a symbol of Ca. I find that Ca on the periodic table. There it is, and it is element number 20. So that is the atomic number. Okay, then we also know that the number of protons is equal to the atomic number. These are always going to be equal. And then to get our number of neutrons, we're using that same thing that we did before, right? It's going to be our mass number minus the number of protons. Okay, so for this specific example, we've got 41 minus 20. That's giving us 21 neutrons. All right, now your go. Go ahead and enter for chlorine 37. You can just list the numbers in order. All right, so hopefully that went okay. Now I would like you to think about this question. Right, so again, barium, element Ba, find it on the periodic table. It's got 56 protons. I'm telling you the question, 80 neutrons, add them together, that gets you 136. So that's protons and neutrons. Where it can start getting a little trickier is electrons. And so my advice to you when you think about these electrons is to use common sense. So we know that if something is neutral in the world, then the amount of positive stuff is the same as the number of negative stuff. And so when we're talking about atoms specifically, that means that the number of protons is equal to the number of electrons, right? Protons are positively charged, electrons are negatively charged. So if you have 5 protons and you need something to be neutral, then you need 5 electrons. Okay, so if something is neutral, then your protons and your electrons are going to be the same. Neutral. Electrons equals protons. Fantastic. Then you have an equation there that uses absolute value, and it will work, and it's great. But again, I think logic weighs out the math here, which you'll rarely hear me say. But if we know that something is positively charged versus negatively charged, then we know there's either more or less negative things in there. Reminder, you cannot change the number of protons for an element. So if you are talking about aluminum, whether it's positive or negative, whatever, the number of protons for aluminum is always going to be exactly the same. So you cannot change that. Okay? What you do change is you make it either more or less electrons if something is negatively or positively charged. So the language I strongly suggest you use is that if something is positive, then there are that many less electrons. And if something is negative, there are that many more electrons. I'll say it again. If something is positive, there are that many less electrons. And if something is negative, there are that many more electrons. So for example, if you're talking about boron with a +3 charge, that +3 right there is telling you that there are 3 less electrons, whereas if you were talking about something like nitrogen with a -3 charge, then you are saying that there are 3 more electrons. Okay, so the way we think about that, right, boron is element number 5, which tells me that it has 5 protons. Because it has a +3 charge, that means there are 3 less electrons. So that tells me that there are 2 electrons in this example. Back to nitrogen. All right, so nitrogen is element 7 on the periodic table. So that means that it has 7 protons. Because it has a -3 charge, then I know there are 3 more electrons, right? Because electrons are negatively charged. So if something has a negative charge, there's more negative stuff in there. So it becomes 10 electrons. And there we go. So that's how you're going to be determining protons, neutrons, and electrons in the atom. So go ahead and think about the following. Right, y'all. So that wraps up everything about what's going on inside the atom, and that's going to lead us into our next unit of talking about isotopes.